All right, 1.5 is our last section in chapter 1, and it will kind of conclude our discussion of limits. And we're going to talk in this section about infinite limits. So infinite limits are the idea of what happens as we go to the edges of the graph. We go far, far to the left or far, far to the right. And they also talk about what happens when we have those locations that have asymptotes. Both of those fall into the category of infinite limits. So we're going to start with a more formal definition of that. Let f be a function that's defined at every real number in some open interval containing c, except possibly at c itself. The statement, the limit as x approaches c of f of x equals infinity, means that for each m greater than 0, there exists a delta greater than 0, such that f of x is greater than m whenever 0 is less than x minus c is less than delta, and a similar statement can be made for each n less than 0. It's long, but it should sort of sound like something you've seen before. Does it? Looks a lot like the epsilon delta definition when we didn't have infinity involved, right? Yeah, except we've got this capital M and this capital N business going on. That part's different. So jot that down. I'll give you just a second because there are several things even to fill in. And I'm going to draw a picture so that we can piece it all together and make sense of it. If I'm using another screen or not. Nope, we'll use this screen. Okay, so if you're still writing, feel free to keep doing so. Let me draw a picture of what's happening here. You've got a big old giant space on yours. Okay, so we're going to draw in an axis. And we're going to draw a location, or a graph that has a location where that C possibly doesn't exist. That's what it's describing, and that's talking about an asymptote. So something like this going on. And this spot where we have the possibly does not exist, we're calling it C. Okay, so what it's saying is that for every m greater than 0, so some upper limit value, like this, if I were to trace over from here, like this, there is some interval. Okay, that's not good because I didn't draw it well. Let's try it moving over my C so it makes more sense. Of course, that's not going to work. There is some interval surrounding C that if I get close enough to C, I'm above M. So I'm in these regions up here if I get close enough to C. And that interval that is happening around C, mine doesn't look great in terms of it being evenly distributed, but that interval around C is that space delta. So this piece and this piece here, let me use a different color. Maybe yellow. Maybe not. Red? That's not bad. They're so tiny. But these spaces right here that are happening are delta away. So it's delta to the left of C, delta to the right of C. And no matter how high I go, right, so like the M is right here, but if M went higher, it'd still be true. It would just make the interval around C tighter, right? If the M had been lower, the interval around C could be broader. It could be wider, and it still satisfy all the conditions. And what this is saying is the same thing is true if the interval were, if this graph were flipped upside down and the N value were decreasing, right? Like I had an asymptote that was going downward instead. Or if I had one that was going up and one that was going down, there would be an upper limit for an M and a lower limit for an N. All right, that's what this is describing. And it's all going back to the idea that we're dealing with asymptotes here. So if I get close enough to the C value, my limit goes to infinity. Why does it matter? Well, when we've talked about limits not existing, we've talked about them not existing for lots of reasons. One of the reasons limits don't exist is if the left-hand side and the right-hand side have a jump in the graph, right? Another way that they don't exist is if they are oscillating, right? And we've had graphs that have gone up and down, and we're talking about what's happening to those kind of limits, right? What if it just keeps going up and down? But this one right here is unique. If the limit is an asymptote, we can actually say, I know how it fails to exist. It fails to exist because it's going to infinity. That's how it's failing. And so instead of saying that it fails at that point, we define it to simply be the value of infinity. So it says, be sure you see that the equal sign in the statement, the limit as x approaches c of f of x equals infinity, does not mean that the limit exists. On the contrary, it tells you how the limit fails to exist. That's what I was trying to get at. By denoting the unbounded behavior of the function as it approaches that specific x value. So we write equals infinity, even though infinity is a concept and not a number. We write that it equals infinity, all the while recognizing that it still is not existing. We're just defining how it doesn't exist. All right, let's do one example and we'll stop for today. This one says, determine whether f of x approaches infinity or negative infinity as x approaches 4 from the left and from the right. Now clearly, if I try to just plug the number 4 into this equation, what will happen? Denominator is 0. And the denominator will not have the ability to cancel out with anything in the numerator, so I definitely have an asymptote here, right? Yeah, I do. And so we have a couple of different ways that we can do this from a perspective. We have, well, 3 actually, because we've done all 3 of them. We have algebraic limits, that's the last one we did. We have graphical limits, we can look at a graph, and we have numerical limits, we can look at tables. And if it doesn't tell you how to decide, you get to pick how you're going to decide. But if you were doing this on like a test or a quiz, you have to tell me how you decided. So if you looked at your calculator and did a graph, you're going to draw the graph. If you looked at your calculator and you looked at tables, you're going to write down the tables. If you simply plugged numbers in, you're going to show me what happens when you plug numbers in, that kind of stuff. So you have to verify it with whatever method you're using on your paper as well. All right, so let me actually do a couple of them for you. Because I can't physically plug the 4 in here, that's not a good option. Algebraic doesn't work for this, right? I can't plug in 4. So in this one, I'm down to 2 options. I have to do either the numerical or I have to do a table. So let's do, I didn't say it right, numerical or a graph. So let's do both of them and you can see what they would, reminders, see what they look like. So let's do a graph first. So if you were to put this into your calculator and you were to graph it, and you're welcome to do so if you would like, your graph will look something like this. It won't have the dotted line I'm about to draw, but for my drawing purposes, it'll help me. It'll look something like this. Okay? Make sure I've got the direction of that right. Just a second.
That's right.
Is it? Okay, thank you. Just doubting myself from what I had drawn earlier. Okay. So the question says, if this is our graph and we're using it from a graphical perspective, it says what happens as x approaches 4 from the left and then also from the right. So we have to write that down. We're going to do the limit as x approaches 4 from the left of our function. You can just write f of x or you can write the function out. And the limit as x approaches 4 from the right of f of x. Okay, so from the left means that I am over here. And as I'm tracking along my red piece right here and I'm going in this direction, is it approaching infinity or negative infinity?
Positive.
Yeah, positive infinity. So this one is positive infinity. And if I do the same thing, but I go from the left, it's the blue one that I'm marking, what's happening? Yeah, down. It's negative infinity. So this is all you'd have to do to verify it from a graph. You draw the graph and you show that the graph is doing these behaviors. You don't even necessarily have to draw the little arrows on it like I did. I'm trying to guide you through it in case you're not seeing the pieces I'm thinking about. But you're verifying it from the graph. You've got your infinity and your negative infinity. If you want to do it from a table point of view, remind you what happens with that one. So the second option is to do it from a table. We call that numerical. And you create a table that does the same thing, by evaluating numbers from the left and from the right. So if my x is going to be here and my f of x is here, numbers from the left of 4 would be like 3.9 and 3.99 and 3.999. Okay, this would be verifying from the left. And if we do it from the right, we'd have values like 4.1, 4.01, and 4.001. And we'll run those real quick. I don't have those written down. So negative 1 over x minus 4. And I'm getting lots of powers of 10. That doesn't always happen, but that's okay. So this is 10, 100, 1,000. And then I have negative 10, negative 100, negative 1,000. And if we put in like 4.0001, it'd get even bigger. So as we're sort of going down these tables, we'll do the first table. What's happening as I go down that table? It's getting infinitely large, right? And if I go down the second table, it's getting infinitely large and negative, right? So we get negative infinity. So again, this verifies this piece, and this one would verify that piece from a numerical perspective. Any questions? You don't have to do both. You're just doing one or the other. It's just you get to pick. So I want to make sure you see what your options are. Okay, so we will table 1.5 for now and pick up with it next class.